This next section, 8.6, is numerical integration. Now, this picture here really demonstrates the concept. This splits up, hide that. This demonstrates the concept of splitting it up into separate pieces, specifically trapezoids. And then based upon that, you will find the area in between.
How's that better?
You can't solve all integration problems. Now here, it talks about the area of the ith trapezoid. So it gives us a formula. And then, just like you remember way back when you covered trapezoid rule, where you got your limit as n goes to infinity, and then you're adding them all together. So this shows you how the formula is derived. Now we're going to look at simple examples, and that's what will be on the quiz next time and test is simple ones. I won't put real hideous ones because they're just brute force. So if you're looking at it and thinking, well, I can do that by regular technique. Yeah, you can. That's not the point here. Now here's the trapezoid rule, and not everything is presented here. Once we show a picture, you'll understand more about it. But let f be continuous on AB. The trapezoidal rule for approximating the integral from a to b of f of x dx is given by this formula here. So it's approximately equal to the b minus a over 2n times f of x naught plus 2 times f of x1 plus 2 times f of x2 all the way up to 2 times f of x sub n minus 1 plus f of x sub n. And moreover, as the n goes to infinity, the right-hand side approaches the actual value. If you were going into mathematics, I think the only person that was majoring in math is gone tonight, but if you're going to that, you would take a class where you would be studying numerical methods for doing this. Because we've seen some techniques, but there are just some integrals you can't do with those techniques. You know, these are all designed so you can use certain techniques. In real life, you probably won't have problems come out perfect where you can use the techniques you've seen. You have to use numerical methods. As engineers, depending upon what kind of engineer you're going into, electrical engineers, they like to use, MathCAD, and they'll just type in the function, and it'll give them the result. So, okay. So let's take a look at, since I'll probably assign the evens as a quiz, so let's take a look at some odd ones. I was going to make them up, but it's so easy mistakes in these. I thought, I'm going to do it this way, and then we can compare the result against CalTech. See if I screw up. Definitely, if you see me mess up, then let me know. It's not hard. It's just basic algebra. Okay, so we got 3. 0 to 2. x squared dx and n is equal to 4. Now, if I were to graph this, at least the part where it's from 0 to 2, if I put 0 in for x squared, that gives me 0. If I put 1 in for x squared, or in for the x, that gives me 1 squared or 1. If I put 2 in, 2 squared is 4. Got this picture right here. They probably gave you a good picture in Calc Chat. That's number 3, number 3. Where they give you no picture. Okay, so from our formula, the trapezoidal rule is given by this right here. N is equal to 4. Now A is going to be our lower number. So A is going to be equal to 1, 1, 0. And B is going to equal to 2. We want to split this up into pieces. Specifically, it says N is equal to 4. See over here how they left this one off. But you have 1/2, you have 1, and you got 3/2. So we're splitting this up into 4 pieces like this. Now, what we're trying to find here is trying to find out what these values are down here. Well, this one here is obviously 0, isn't it? This one over here is obviously 2. Now, I know you can look at these and see them. You know, here's 2. They don't actually write it out here, but there's 0 here. You can see it's 1/2, 1, 3/2. But how you get that is the change in x is equal to b minus a over n. So you got 2 minus 0 over 4, which is 2/4, which is 1/2. When I say delta x, that's this distance right here. So if I had 0 here, 0 plus 1/2 would give us 1/2. 1/2 plus 1/2 would give us 2/2 or 1. And then 2/2 plus 1/2 would give us 3/2. 3/2 plus 1/2 gives us 4/2 or 2. Is that good so far? Really, that's the hard part right there. Now our formula is approximately equal to b minus a over 2n. That's different than delta x. Delta x is what we use to figure out what these values are here. Times f of x naught plus 2 times f of x1 plus. Now these are going to go up to n. Our n is 4. Now all of these have 2's in front of them except for the beginning one and the ending one. So this is going to be 2 times f of x2 plus 2 times f of x3. And our last one, the n is equal to 4, is going to be plus f of x4. Should try to draw this bigger next time so you can see it a little bit better. This first one is our x0. This next one is our x1. This is our x2. This is our x3. And this is our x4. So b was 2 minus a, which is 0, over 2 times n, and n is 4. F of x0, which is 0, plus 2 times f of x1, which is 1/2, plus 2 times f of x2, which is 1, plus 2 times f of x3, which is 3/2, plus f of x4, which is 2. Recall our function, f of x is equal to x squared. That will always be whatever's inside this interval right here. That's your f of x. Okay, so 2 minus 0 is 2. 2 times 4 is 8. Or 2's cancel 1/4. F of x0. We're going to plug 0 in for x in our function. So we're going to have 0 squared plus 2. And here we'll plug 1/2 in for our x. So that's 1/2 squared. Here we'll plug 1 in for x. So that's 1 squared. Here we'll plug 3/2 in for x. So that's 3/2 squared. And here I'll plug 2 in for the x, and that's 2 squared. Keeping in mind, your middle items have 2's in front of them, and the first item and last item don't have the 2. So that's 1/4. 0 squared is 0, so that drops away. 1/2 squared is 1/4 times 2, 2/4 or 1/2. That gives me 2. This is 9/4 times that is 9/2 plus 2 squared, which is 4. 1/2 plus 9/2 is 10/2 or 5, plus 4 is 9, 11, which then gives us approximately 11/4. 2.75. Assuming I didn't screw up in the basic math somewhere. Now, if I went back and did that by hand, we would have 0 to 2 x squared dx. So add 1 to your power, divide by your new power. Plug those in, and I got 2 to the third, which is 8, 8/3. gives us 2.67. So it's a little bit off there, isn't it? Assuming I didn't mess up math. Let me double check that. I'll check. 2.75. Okay, I didn't screw that up. You can see why I'm not going to give you a very hard one on the quiz or the test, because it's just tedious. It's not hard, it's just tedious. Now that is our first one, the trapezoidal rule. I'm going to show Simpson's rule next, but is there any questions on that? Are we good on that one? Okay. Okay, I'm going to try to undo some of this. Okay, so Simpson's rule is given by this. You see it's b minus a over 3n. You got f of x naught plus 4 of x, f of x1, then plus 2, then plus 4, and then it alternates until the last one doesn't have a number in front of it. So we're going to have b minus a over 3n. First one doesn't have a number in front of it. The last one doesn't have a number in front of it. So I'll put it over here. And notice the last one is based upon n. Our n was 4, so that's why I put f of x to the 4. And now it alternates. It starts with a 4 in front of it, then 2, 4, 2, until you get to the last one. And starts at 4. Okay. Plus 4 of f of x1 plus 2 f of x2 plus 4 of f of x3. Oops, got a plus there. And then plus my f of x4. Now you'll notice in some of these formulas, they will tell you that n has to be an even integer. We didn't have that stipulation on the trapezoidal rule. You know, if you look over here, it doesn't say anything about n, does it? But in order for this alternating to work, because it has to start with a 4 and has to end with a 4 here, then you have to have an even number. Okay, so remember, this is our x naught, x1, x2, x3, and x4. So b is 2, so I got 2 minus 0 over 3 times n, and n is 4. We got f of x naught, which is 0, so that's f of 0, plus 4 times f of x1. X1 is 1/2, plus 2 times f of x2, which is 1, plus 4 times f of x3, which is 3/2, plus our last one, f of x4, so f of 2. Did I miss one? Ah, I did, didn't I? 2. Where in the world did that come from? Oh, that's the F should be right there. Yeah, you're right. You can see why I brought up CalcChat. Canvas size. And this might even be one like on a test where I just tell you to do the setup and stop. Like stop right after you plug in your numbers. I think I did that on one of the problems the last test, didn't I? I said do the setup but don't solve it. Some of you went ahead and solved it, had fun. But you didn't have to. I don't even know if you could solve it, to be honest. That was number 5. Yeah, it's if you can find the integral of that, you're a better person than I am, because I don't think it's solvable. But the setup is what I was great. Okay, so 3 times 4 is 12. 2 over 12, that's 1/6. I'm gonna plug 0. Now we're still dealing with that function hasn't changed, x squared. I'll do a little bit more harder one on the second example. So I'll plug 0 in for the x. So I got 0 squared plus 4 times, plug the 1/2 in for the x, so 1/2 squared, plus 2 times, I'll plug 1 in for the x, so I got 1 squared, plug 3/2 in, 3/2 squared, and I'll plug 2 in, I got 2 squared. 0 squared drops away. 1/2 squared is 1/4 times 4 is 1. 1 squared is 1 times 2 is 2. 3/2 squared is 9/4 times 4 is 9. And 2 squared is 4, assuming no basic math mistake. 13, 15, 16, 6. 6, 15, 16, 6, yeah. Or 8/3. Which is our 2.67. And that matched our integral pretty much exactly, didn't it?
0.02.
Is it off at 0.02 at the very end? Oh, you're talking about the trapezoidal rule. Okay, now I wouldn't say that the Simpson's rule will always be, spot on. It probably is for a very simple example. But as I indicate, as you take n to be higher, your approximation gets better. Now I couldn't tell you what this is doing, but when I come here and I put x squared in, and we do the second trace, and we choose number 7. And it asks us for our lower limit. You put 0 in, press enter. You put in your upper limit 2, press enter. And it gives us this. This is either doing the trapezoidal rule or it's doing Simpson's. So that's what it's doing when you've been doing that so far this semester. Actually, since it's, well, no, I don't know how many intervals it's choosing. Because if you do more intervals on trapezoidal rule, you'll get better approximation also. Questions on that?
What would a harder problem look like?
Let's take a look at a harder one, make it a little bit more interesting. This one started as 0, so the offset is not that it's challenging, but you'll see that too. I'll show one of those.
No, that's in that section.
Yeah, I'm gonna. I'll show the formula for figuring the error, but we're not gonna really be programming this. So I just want to show the formula. I'm not gonna have you do any work on it, or won't be on a quiz, won't be on a test. Now the trapezoid and Simpson rule will be. So, yeah. Though I'm not going to sit there and have you do mindless calculations. It'll be more part of the setup, just like that. Set it up and stop. Okay, so let's pick a harder one. Number 9 would be good. You might think that 11 and 13 are harder, but they both start at 0. I want to show one starting at number other than 0. So let's look at number 9. Okay, so from 4 to 9. This one's actually harder, the hardest of all of them, probably. In terms of brute force, because well, what's in here? 8. So you got 8 of them to do instead of like 4. So 13's a little bit easier, but that's okay. We'll do this one. That's okay. It won't be bad. Because I'm not gonna do the Babylonian method for doing square roots. I'm gonna plug it all pretty much in my calculator anyway. So. Okay, so let's come back here. Now you can graph it, but really, we're trying to figure out what our x's are. Is that big enough? Okay. So here's our first one, and that's going to be x naught. And that's starting at 4. Now, our next one, remember our delta x is equal to b minus a over n. So we'll have 9 minus 4 over 8. Is that really 5/8? 9 minus 4 is 5 over 8? Surely I didn't pick the hardest thing. Man, looks like they're adding 8s. Okay. So this next one here, our x1, we're going to take 4 plus 5/8. That's 37/8. 32, 37, 37/8. Okay. Now that I got that first one, the rest won't be too bad because I'm just adding 5/8 over and over. So 37 plus 5 is 42/8. I could simplify that, but since I'm going to plug it in the calculator anyway, then not much use. My next one, x3, I'm going to add 5/8, which gives me 47/8. My next one, x4, I'll add another 5/8, which is 52/8. Next one, I'll add 5/8, which is 57/8. X6, another 5, that gives me 62/8. Add another 5, that gives me 67/8. Add another 5, that gives me 72/8, which simplifies to 9, which is where I wanted to end up. I wanted to end up at 9, didn't I? And you see, we got 1, 2, 3, 4, 5, 6, 7, 8 divisions, which is what we wanted because the n was 8. So it's kind of a check. You know, when you go through and you keep adding it over and over, you better come up with this many divisions, and you better come up with the ending number. If you did this b minus a over n correct, and you're doing all this basic math correct. Okay, like I said, that's kind of the hard part there. Let's see, the trapezoidal rule. So we got approximately b minus a over 2n, and remember our first one and our last one don't have a numbers in front of them, but the others all have 2's in front of them. So we're going to have f of x naught plus 2 of f of x1 plus 2 of f or f, 2 times f of x2. I'm not going to keep saying that, so I'm going to screw it up. And then our last one, which is the fn from our formula, doesn't have a number in front of it. So that's f of x8. Okay. Keep in mind that your f of x is equal to the square root of x. That's this right here. So now, plug in everything I've identified. B is 9 minus a, which is 4, over 2 times n, and number of divisions was 8. Now, x naught was 4, so I'm going to plug that into the square root. So we got square root of 4 plus 2. X1 is 37/8, so we're going to have a square root of 37/8 plus 2 times x2, and I'm just going to actually plug these in. So I'll quit saying it. 42 over 8, 47 over 8, 52 over 8, 57 over 8, 62 over 8, 67 over 8, and our last one, the 9, we don't have a number in front of it, so it's the square root of 9. My big question is whether they actually come up with just the decimal or they come up with the value. Let's see. Okay, good, just the decimal. So I'm going to just plug this in my calculator. Again, on the quiz, on the test, even if I forget to say it, this is all you have to get down to. Once you plug in a number, stop right there. You don't even have to plug in your calculator, unless you just want to check yourself. Because if you plug in your calculator, the value you get should match if you use that the function under the second calc. Okay, 9 minus 4 is 5, so I got 5 divided by 16. Okay, so square root of 4, I'm going to put a 2 in there. I can do that one in my head. Plus 2 square root of 37 over 8. Plus 2 square root of 42 over 8. I'm going to show you an alternative way of doing this in a second. Plus 2 square root of 47 over 8. Plus 2 square root of 52 over 8. plus 2, 57 over 8, plus 2 square root of 62 over 8, plus 2 square root of 67 over 8, plus 3. Did I not put a closing parentheses after this 8? Unless it's just not showing it. That's just great. I didn't put a closing parentheses there. That would have screwed it up right there. Okay, insert closing parentheses. I think everything else is okay. Let's see if that's a true statement. Ah, that looks good. Almost screwed it up. 12.664. Okay. Is everybody good with that part? Now on your calculator, and this is beneficial if you got a really complex that you're working with. Every one of these you could do with the techniques we've seen, except for possibly number 13. That might, no, that would work, because we could use that table method I showed you, yeah, so that could solve it. But number 14. I think integration by parts on that, I think that would, so I think all of these you could actually use the techniques we've seen so far. I'm sure there's some that you can't. Number 22, I don't think you could do it all, so you have to do it using this technique. But if you got something more complex to put in, go put your function in the y equals first. So this one was square root of x, like that. And then I'm going to exit out. Now we're wanting to type in this with the numbers plugged in. So b minus a, that's again 9 minus 4 is 5 over 16. So I do 5 divided by 16, beginning parentheses, and then we want f of x naught, which x naught is 4. Now how you get that function notation is you go to vars, you go to y vars, you go to function, and there's y1, and then you can put your beginning parentheses and 4. Plus 2, and then we want to go to vars, y vars, function, y1, beginning parentheses, x1, which is 37 over 8. Plus 2 vars, is that any easier? You're probably right, it's probably harder. But if I, yeah. 37 over 8, next one's 42 over 8. Vars, y vars, function, y1, beginning parentheses, 47 over 8. Plus vars, y vars, function, 52 over 8. Jeez. I knew this section would be easy, but I knew it'd be very tedious also. I forgot the 2, didn't I? Well, you get the idea. So we go through there, and when you did that, that would give you, assuming I typed it incorrectly, you get the same result. So is it easier? I don't know. What? Yeah. Oh, is that? Oh, for each one. Oh, okay. That's worse then. Anyway, I'll go ahead and clear that. Now we still have the other rule to do. So let me back this on up to get back up to this point. This one I'll just do the setup. I won't actually plug it in the calculator. Okay. So Simpson's rule. B minus A over 3n. B was 9 minus A, which is 4, over 3 times n, and number of intervals was 8, times f of x naught. F of x naught is 4. Now it's got to end with f of, f of x8, which is 9. So remember, your first one and your last one are just your x naught and your xn, in this case x8. All the rest alternates, starting with 4, then 2, then 4, then 2, then 4. So this is going to be plus 4 f of 37/8 plus 2 f of 42/8 plus 4 f of 47/8 plus 2 f of 52/8 plus 4 f of 62/8. I'm screwing something up. 57/8. Plus 2 f of 62/8 plus 4 f of 67/8, and then plus f of 9 at the end. 37, 42, 47, 52, 57, 62, 67, and then our last one. Okay. Keeping in mind that for this particular problem, our f of x was square root, I think. Square root x. Then 9 minus 4 is 5. 3 times 8 is 24. Plug 4 in, so I got square root of 4 plus 4 square root of 37/8 plus 2 square root of 42/8 plus 4 square root of 47/8 plus 2 square root of 52/8 plus 4 square root of 57/8 plus 2 square root of 62/8 plus 4 square root of 67/8 plus square root of 9. Nobody's going into programming in here, are they? Computer engineering? Oh, okay. What this is like a for loop. So each one here is a pass through the for loop. And what you're increasing, of course, you're alternating the 2 and 4. and then you're increasing it by that the delta x each time. So it's something you actually program. Yeah, it is. Yeah, it's kind of a fun one because it's not even really complex like when the signs change or anything. You just have to have something different for your first one and for your last one. And that you could do, well, this you could set with just initially when you declare the variable. And this one you could check, well, actually you could have your for loop go to one less, go to n minus one, and then that you just add on after the loop. Anyway. Okay. Questions on that? Okay. Let me talk about this formula, and I'm not going to work one of them. Well, actually, two formulas I want to talk about. Here's a formula that if you're trying to find the integral of a quadratic, p of x is equal to ax squared plus bx plus c. Now, do you see a problem with this? I hesitate to even cover it. I'm not going to show an example of it. How hard is it to find the integral of x squared and x and a number? Super easy, right? Add 1 to your power, divide by your power. Something you saw back, the second week in not second week, because integrals are at the end. But anyway, you saw it, as one of the easiest problems you saw back in Calc 1. But anyway, here's a formula where you don't have to do that. And again, you might wonder, well, then what's the purpose? Well, if I was going to program it, this is super easy to program. So it kind of goes back to that too. Anyway, that's that formula. Okay, errors in the Trapezoidal Rule and Simpson's Rule. If f has a continuous second derivative on AB, and that's why I don't really focus on this very much in this class anyway, because the idea is that you're programming this, and to program the derivative is not so easy. Remember the technique for finding the derivative from Calc 1? For finding the derivative. There's a algorithm for it. In terms of thinking about programming it. Let's see. Not there. Assuming they haven't taken out of the book. There it is, Newton's method. Remember Newton's method? No. What is it? It's not Newton's method. There is a numerical method for finding it. So if you're trying to program it, you try to write a program to get the second derivative, because if you have to do it by hand, that defeats the whole purpose of picking up a computer program or calculator or whatever. So if it is continuous, then the error E in approximating the integration by the trapezoidal rule is given by this. So the absolute value of E is less than or equal to. Less than or equal to implies this is an absolute value inequality, which, remember the absolute value inequality, you have like this. Then this is between these two values here from college algebra. So it says you can have an error going, on both sides of that type of deal, like a range. And the goal is to reduce that range to as small as possible. But it's equal to b minus a over 3 all over 12 n squared. Now here's the challenging part, because you'd have to, with what we know so far, and there is a way to find a derivative using numerical methods. I'm drawing a blank. But you find your second derivative and you maximize it. Remember where you set it equal to 0, find your critical values and all that. Then, if you're talking about Simpson's rule, your absolute value of E is less than or equal to B minus A to the fifth power over 180 into the fourth times the maximum of your fourth power. Well, if you have anything complex, is it very fun to find a fourth derivative? Or not fourth power, but fourth derivative? Horrible, isn't it? If you got something easy like a nice polynomial, then yeah, it works out really nice. But anyway, I'm not going to sign any of those. Questions on any of that? Well, we're done with that section. If you want to go ahead and take a break, then we'll go on to the 8.7, which is another easy section. So there'll be time at the end of that tonight. So if you're struggling with anything in the past, then I'll answer any questions you have of those, show examples or whatever. So, yeah, it'll be fine.
What's the next test?
We'll finish the chapter on Tuesday. I guess I'll throw it for a vote for you guys when you get back if you want it that Thursday or you want it the following Tuesday. So think about it while you're on break.